Hello, today's section is 5.4 and the topic is equation and graphs of trigonometric functions. So to get warmed up, we're actually going to be looking at a question from section 4.4. And the question is sine x equals to 0.5. So remember 0.5 can also just be written as 1 over 2. And since sine x is all by itself already, we can just go ahead and figure out the fact that our terminal arm is in quadrant 1 and quadrant 2 because the sine ratio is positive. From here, we're going to find our reference angle. Remember, keep the ratio positive. Well, it's already positive. And our reference angle is pi over 6. This is one of our special angles, right? So that means we know this part is our reference angle, this part is our reference angle. So we have two standard position angles from the initial arm. Here is angle 1, and here is a second one. So the first one is just going to be the same as our reference angle, and the second one is just going to be pi minus pi over 6. Okay. By the way, I'm just choosing to write in radians. Since this question didn't specify, if you wrote in degrees, that is okay as well. So that means we're at 5 pi over 6. Since there is no domain being restricted, I'm just going to write out the general solution. Or solutions in this case. So we have pi over 6, since we're looking at the coterminals of that, so we're just going to add and subtract 2 pi n. Or just add, since we're going to say n belongs to all integers. And we also have 5 pi over 6 plus 2 pi n. Okay? There we go. Okay, so that was 4.4. But now in chapter 5, we can solve this graphically. So I'm just going to write back, so we were looking at sine x equals to 0.5. So there's kind of two strategies going at this. The first one is to treat this as two different graphs. So this left side, we're going to call it graph 1. And the right side, I'm going to graph in green, which we'll call graph 2. We're going to graph both of these graphs and see where they intersect. So graph 1 is basically just the base sine graph. I'm going to say 1 is 2 boxes. Okay. And for sine, y-intercept at 0. The entire period is 2 pi. In the center, we're back at the x-intercept. First half of half of the first half, we find our max. Half of our back half, we have a min. And from here, we're just going to connect together. I'm going to go around here. Try to make a nice curved line like so. Okay. And the second line is going to be just at half. So one box will represent half, and we're just going to draw a straight line across. Okay. And the points where they intersect, here and here, should be the answer to our x values. And looking back at our algebraic conclusion from our 4.4 method, we know we should be at pi over 6 and 5 pi over 6, which is indeed this each box here. So if we go down, right? This point here does give us x equals to pi over 6. And if we go straight down, this part here is also x 5 pi over 6. Okay, so the 2 should match, the 2 does match. We did the correct work here. Okay, so method number 2 is to look for x-intercepts, or we just move everything to one side and we make that equation equal to 0. So in this particular case, we've basically moved our entire sine graph down. This guy here is basically our D. So let's just move this blue graph down. So front and back. Okay, the middle of our period, everything's just moving down by half and half. Okay, let's just draw it again. And nice curved line. Ha, okay. Now, since we moved everything to one side and we have it equal to 0, we're looking at the x-intercepts this time. So here and here. And as we can see, these 2 points are also equal to the x values that we solved algebraically. So let's move on to a more complex equation with more things going on. Okay, so we're going to be looking at this equation here. 2 sine pi over 4x plus 1 equals to 5 over 2. So first we're going to solve graphically. We're going to look at 2 ways to solve it graphically first. So first is a way called solving by zeros. So solving by zeros basically means the same way or strategy that we used for the red graph above. And we're going to move everything to one side and make our equation equal to 0. So if we move this 5 over 2 to the other side, it's going to look like the following. 2 sine pi over 4x plus 1 minus 5 over 2. And if we kind of simplify that, we're looking at 2 sine pi over 4x minus 3 over 2 equals to 0. So this is the equation we're solving here. So before we start just plotting points, we're just going to figure out some of the key details so we know how to plot things more quickly. So first, we're just going to look for our transformations. So A, or our amplitude, we know is 2. Now, value of B to help us find our period, in this case, is pi over 4. So with that information, we do know our period is 2 pi over B. So our period is 8. Now C, well, we don't have a value C, so no side-to-side movement. And D is negative 3 over 2. And remember, D is just equivalent to our midpoint. So since we know D and we know A, we are also able to find our max and our minimum values. So max is going to be our midpoint plus our amplitude, which in this case is 0.5. And our minimum is going to be our midpoint minus our amplitude, which is negative 3.5. So now with all these values, we can easily plot this graph very quickly. So for my range, I'm just going to treat every 2 box as 1. So here's 1, negative 1, negative 2, negative 3. And for the domain, I'm also going to treat every 2 boxes as 1, 5, 6, 7, 8. Since my period is 8, I'm just going to go out to there. And our midpoint is at negative 3 over 2. And since this is a sine graph, I know I'm starting at the midpoint. So that's negative 1.5. That's where I'm starting. That means at the end of the period, that's where I'm ending. In the middle, I'm going to be also at the midpoint, which is 4. And at half of the first half, I'm at my max, which is 0.5. And at half of my second half, I'm going to be at the min, which is negative 3.5. So at this point, I can just kind of connect my points together. So I'm going to just try to draw my best curved line here. It's gonna look something like that. So basically from this graph, we know that our x value is gonna be where our x-intercept is. So it's gonna be 1-ish and 3-ish. Obviously our graphs are not perfect, but we know the ballpark in which our x values should be. Strategy number 2, solving by intersection. So in this particular case, we're actually gonna keep our equation as is. So keep it as it was before we moved stuff, which was like so. Left side, we're going to have it as graph 1. And the right side, we're going to have it as graph 2. So A has not changed. B has not changed. So we know the period is still 8, okay? C is still 0. D, however, has changed now. Now is 1. So that means my max is now actually at 1 plus 2, and my min is now at 1 minus 2. So it's at 3 and minus 1. Graph 2 is just going to be a straight line. Okay, ooh, realize there's a color confusion. Okay, so I'm just going to do a quick color change, so then it's not going to get confused. I'll graph the left side in green and the right side in blue. Graph 2, okay? All right, I'm going to have the same scale, so each box will represent, or each 2 boxes will represent 1, and each 2 boxes will also represent 1 for the domain 2, 3, 4, 5, 6, 7, 8. Okay, and the midpoint is at 1. Graph 1. Start and finish in the same spot. And the middle will be also at the midpoint. Max is at 3. Min is at -1. And we're going to just try to, actually, I'm going to graph the straight line first. So that is going to be 2.5. It's going to be a straight line going across here. Ooh. All right. And we're just going to connect it over. So I'm going to go up and around and down, and then connect it curve like, not too pointy, okay? All right, and now we're going to look at the intersecting points. So here and here, if we draw a kind of straight line down, yeah, we're still at 1-ish and 3-ish is what we're looking at for our x. So those are the 2 methods for graphically. Now let's move on to solving the same thing algebraically. So we know we should be at around 1-ish and 3-ish if our algebraic kind of solution matches. We know we've done the correct method for both graphically and algebraically. So again, we need to just move things around so we end up with the sine angle by itself, because right now it's not by itself. So 2 sine pi over 4x plus 1 equals to 5 over 2. So first we're going to have to move the 1 to the other side. So that's 2 sine pi over 4x equals to 5 over 2 minus 1. So when you subtract it, we have 2 sine pi over 4x equals to 3 over 2. Now I want to just divide both sides by 2 because I want to isolate this by itself, okay? get rid of the highlight. There you go. So let's divide, oops, still writing in highlight here. Ooh, that's not good. So I'm going to divide both sides by 2. So now I have, so this is gone. So I have sine, oops, sine of angle equals to 3/4. Now please be mindful, this whole thing is an angle, okay? And this guy is, well, our ratio. So at this point, we can draw our quadrant. And since the ratio is positive, we know we're in quadrant 1 and 2. And we're going to find our reference angle. So we know sine of our reference angle is going to equal to the ratio. Now, looking at 3/4, not something we recognize. Not special ratio. Therefore, so not one of the ones we have on our table. Therefore, use calculator and you'll find some decimal point. So our reference angle will be found, so our reference angle will be arc sine 3/4. And that brings us to a reference angle 0.85. So back to our quadrant. Here is basically a reference angle, and here is a reference angle. Okay, so that means our standard position angles will be from initial arm to here, which in this case, again, is the same as our reference angle. So the first one here is just, oops, 1. Is just 0.85. And the second one out to there is going to be pi minus 0.85. But here is where things are different than chapter 4. Remember, our angle, the relationship here is that the angle is actually composed of pi/4 times x. So if we want to find x by itself, we will need to take away that pi/4. So therefore, when we're looking at that first terminal arm in quadrant number 1, x, I'll just call it x1, is actually equivalent to 0.85 divided by pi/4. Because remember, the relationship here is the theta equals to pi/4, right? Pi/x. So in order to have x by itself, I have to have theta divided by pi/4 to get x by itself, which is why I built this equation here. So if I have that, then my answer to the nearest hundredth would be 1.08. And for my second terminal arm, the one in quadrant 2, I'll call that x2. It's going to be pi minus 0.85 divided again by pi/4. And that is going to get to 2.92 if you round to the nearest hundredth. So these are the two possible solutions between 0 and 2 pi. Okay, so the last part here is just determine the general terms for the above equation. So the general term, we know we're going to have the numbers or the angles that we found here, or from the question above, and then we'll need to figure out all the possibilities on the graph. So we're actually going to go back to the graph to help us kind of piece this one together. So looking at this graph here, remember the graph doesn't stop at one period. I just graphed one period, but it's actually going to keep on going. So, you know, here is, 10, oops, not 10. There's going to be 9, 10, 11, 12, 13. And we know when we get to 2 over, we're going to be, once we're 2 over, we're at our max again. When we're 4 over, we're back in the mid. Yeah, so it's going to be like that. So I'm just going to kind of connect it. Oops, wrong color here. Just going to kind of connect it, continue connecting here. So the graph will kind of continue on something like that. And what you're going to see is that this point right here is basically equivalent to this point right here, because our period or our graph has just kind of repeated itself. Now the question is, how far is here to here to know when it repeats itself? And you're going to notice that this distance is basically the period. And every period, the points will repeat itself. Therefore, we could write out the general equation for general terms. It's basically whatever solution you get plus the period n number of times, and again, n must belong to all integers. So the solutions we have in this particular case is 1.08 and 2.92. The period in this case is 8n, and I could just write the same thing, and n must belong to all integers. And that is it for Chapter 5, Equations for Trigonometric Functions.